Hello, I'm Eric Anderson, and this is the Zen Guide to Getting Your Data Ready for Machine Learning and Analytics. Part of Cloud OnAir, the journey from big data to AI. And I'm glad to be here with you. Good morning, good afternoon, good evening, wherever you are. I'll be sharing with you 12 Zen principles. And along the way, you'll find that the biggest difference we're highlighting here between traditional statistics and machine learning is how you deal with outliers. What you're looking at is a zonkey, a cross between a zebra and a donkey. Just to drive home the point that there are outliers, and we'd love for our predictive models to know what to do when they see them. And in order for that to happen, we need to understand and collect those outliers and have them in our sample data sets. Along the way, I'll be introducing how you can do this using Google Cloud Platform tools, including Google Cloud Data Prep. What you see here is one of the public BigQuery data sets. This is worldwide flight data shown in Google Cloud Data Prep. I've scrolled to the right where you can see departure delay and arrival delay. Data Prep provides a helpful set of histograms per column. It also gives you quality metrics and infers type on those columns. So in some cases you can see mismatched values. But our arrival delay and departure delay show an expected amount of clustering, probably around the expected arrival time. What you're looking at is a sample of the data. Data Prep relies on samples in order to have a quick user experience. Let me start by showing you the random sample. Here you can see that outliers aren't as evident. But if I switch to what we call a stratified sample, this sampling is designed to capture all the outliers you would want to see in your data set. You can see the arrival delay is actually much broader than we saw in the random sampling. Using Data Prep, you can control the samples available to you. By default, we generate a first rows or random sample, but there are other options. You can see filter base, anomaly, and the stratified sampling I showed you earlier. These samples, as we help you fulfill the first principle of the Zen Guide, which is to understand and capture outlier examples. Principle 2 is to see the world as it truly is, because the data we see often contains a lot of errors that may have occurred during production. We need to see past those errors. Here's an example of tax data that contains several duplicates. And this we discovered as we prepared the BigQuery public data set for it. We'll talk more about this data set later. But Data Prep gives you the tools to clean data for these anomalies. Using the visual cues, you can determine that there are duplicates. And in this example, it was just a simple step to remove duplicate rows. Our third principle is focused on how we do the machine learning optimization. As you know, it's fragile. Because surfaces are not always convex and sparsity problems are NP-hard, achieving a fit and a robust model is difficult. Usually, we scale, center, and clip data in order to achieve the model fitness we desire. Here's a few examples of how we might do that. So linear scaling, hard caps, min and minimums, or log scaling are common approaches. And let me demonstrate how you might do this in Data Prep. So we're back looking at the flights data we saw earlier. What I'm doing is I'm in the middle of applying a transformation step. This is an aggregate transformation, where I'm going to count the number of rows when I group by the departure airport. This generates a preview below, and you're seeing our new simplified table, which becomes our table when I add that to the recipe. So this count of flights per airport, you can see, is not regularly or normally distributed, and it skews to low numbers. What we might do is take the log. This simple transformation now gives us a much more distributed feature, and we might continue by applying a max, which maybe gives us an even more optimal distribution. I'll leave that for you to decide. There's a lot of debate about how to do feature engineering, but know that Data Prep gives you some of the tools you need to. Principle 3, that's in summary of Principle 3, which is that we need to pay attention to the magnitude and dynamic range of our features. So on to principle 4, and that is, again, in reference to outliers. This is how we make sure that our examples are sufficient for our data sets. Specifically, we need to think about how to handle the real value but out-of-band inputs. In this case, we're back to our worldwide flight data, and you're seeing that, as shown earlier, that those outliers are rare, but having those outliers are valuable to our prediction. One approach is to bucketize the data. This is basically what we saw in the histogram within data prep. Once you apply quantiles and bucket those data, it'll allow you to treat these outlier groups. You'll have a larger supply of outlier data points within each category. This flows neatly into TensorFlow's bucketizing and bucketized column and embedding column transforms. Principle 4 is about finding the truth where you are. This example is the tax data I described earlier. What you see here is the job results page. Earlier within data prep, I showed you histograms per column of sample data. After you apply transformations on a full data set, data prep then gives you the profile of that full data set. It's collecting the profile during the job that creates the full data set. Previously I created a data prep flow that cleaned and processed this data, removing the duplicates we discussed earlier. What you'll notice is that I created a column called population per organization. And you're seeing that it was discovered that one region of the world had a big outlier here, which is the number of nonprofits per capita. So using the job results page in data prep, I was able to observe this outlier and show it here for you on this map. So this is the 4th principle of our Zen guide. Moving forward, you'll find that while it's possible to gather all the embeddings, to learn the embeddings you may want in the data sets you have, it's often difficult. Some embeddings are hard to learn. In this case, reading text to compare countries to capitals could be something you could infer with machine learning, but it might be better to just bring in a mapping table or bring the embeddings from somewhere else. Principle 6 is all about bringing data together. This is an example of weather data and taxicab information. With a simple Python command, we can merge weather data and trip data on a join key. This gives us additional features to work with in our modeling. This could also be done in data prep, as demonstrated earlier. Let me show you how a join would look. This is the flow details page in Google Cloud Data Prep. You're seeing here the tax information and population census data set. Here's the recipe where the join occurs. I'll step you through this. At this point, I'm going to add a new step, a join. From the join screen, I can select an additional data set. Here's where we want our census information, our population by zip code. Let's preview the data set. Okay, so you're looking at zip code and population. I'm going to select join keys. Already, data prep has inferred the likely join key in this case. So I have nothing additional I need to do here. Now I just add any columns I want to bring into my final data set. This is the work that was done necessary for me to generate the job results page you saw moments ago. Once you've done your feature engineering, you'll want to apply these changes to an entire data set. Up until now, we've just been working on a sample. This is done with the Run Job button. Here we can create a BigQuery or GCS table, with the options being that you can append, truncate, or replace a given table. This is set up to replace a results table in my BigQuery dataset. I select Run Job. At this point, data prep takes the script configuration that we've assembled through our recipe, if you will, creates a cloud data flow job, submits that to data flow for execution. This is a previously executed job, and we can select here to view the results. Here we can see a profile of the entire job. But what we'd also like to do, probably, is schedule this job to be executed on some regular basis. Perhaps every time the flights table is updated, we'd like to execute our feature engineering work to produce our downstream table. From the flows view, we can add a schedule. Schedules are done on the frequencies you'd expect with per minute granularity. So this could be done daily, as I suggested earlier. Or if there was any reason, we could also do this hourly. Even cron expressions are supported, if you'd like a more complex description. Once we've set up a schedule, we then need to set the destinations. Data prep allows you to have a development destination, which is what we've been using up until now. That was the table that I was replacing with the job we just executed. And then we could have a scheduled destination. This involves the same publishing actions as before, so we won't go through that. Let's go look at how our job is progressing. We can go list of all running jobs. Here's the transform that's been running. We can go look at the details of this job as it's executing. This will open a window into Cloud Data Flow's monitoring page. There's no reason we should have to come here. All the information we need to execute our job and monitor it are available within data prep. But if you'd like to know more information about how your job is executed, you can come here. This gives you the layout plan of how all the logical steps are executed either in series or in parallel, and also provides you information about consumption of resources. Let's go back to the job that is just completed. Here you're seeing the auto-scaling profile. At some periods of our execution, we didn't need as many workers, but in other periods when we did, the job auto-scaled for us. If there were any errors available during the job, you could find them here and search for them using the logs viewer. This job appears to be running just fine. We can go back to our flows page to look at the scheduled destinations. As mentioned, we've set up one destination to BigQuery. Let's set up some others. This is flight data. Once we have a scheduled destination, this flow is now scheduled. We could set up more data sets to be scheduled within a single flow on the same frequency. You can see which data sets are scheduled with this little clock icon. This allows us to develop feature work in an ad hoc manner, as we've just shown you, and then to more or less check this into production. I've now moved this job from something I do on my own machine, on my own data, to something my whole team can benefit from by publishing these data sets in BigQuery on a regular basis. We've talked mostly about handling outliers, but a big key in ML is the idea of how you handle your various data sets. You'll have to split your data set into training, validation, and testing data. And there's a process to this. Of course, the goal being, or a constraint being to not overfit your model or underfit your model. One part of this is that, or a common mistake is to use just naive random splitting. Here I'm giving you a demonstration of how you could do naive random splitting in BigQuery. While the random function is tempting, you'll see that this is not repeatable. You'll get different results each time. A better approach might be to use a hash on a well-distributed column. So in this case, you're seeing a code snippet for how to generate a hash on such a column. This will give you repeatable training and validation data sets for use elsewhere. The seventh guide, you only lose what you cling to. The seventh principle. All right, so let's move on to number 8, which is where you get involved. You don't, as a human in this process, you don't only bring your ability to manipulate the data set, but you also bring your own insight. We think it's an important principle to apply what you know to a situation. For example, as you apply feature crosses, you can think about how you can introduce your own insight to the situation. In this case, you understand the geography and know where lat-long distributions would be appropriate on a given map. Be deeply aware that the world is impermanent. So what we mean by that is that it's important for you to build for change. And the Google Cloud products have been designed to do so. We've talked a little bit about data prep and how it can be used. Data prep runs on Google Cloud Dataflow. And here you're seeing how Dataflow can be used to ingest a stream pipeline or ingest data from cloud storage, a stream through PubSub, or batch data through cloud storage. These can be written to either BigQuery or Bigtable. And using Google Cloud Machine Learning, or an environment like Data Lab with Google Cloud Machine Learning, you can apply some of the principles we discussed previously. What's great is that now you can do this continuously, whether across batch or streaming, which allows you to build for change. We're moving on to our 10th principle. That is how you handle faults. We don't need to be afraid of having faults. They can help us improve. But it's important that we shuffle our faults across the data set. Principle 11 is about using serverless infrastructure. So earlier I described how the Google Cloud products can help you have a batch and streaming pipeline, meaning you can do things in development mode and then stream them quickly in production. This topic is more about the fact that you don't have to manage that infrastructure, whether it's in batch or streaming. The serverless products in Google Cloud allow you to focus on the machine learning and analysis aspects and leave infrastructure to someone else. We're on to our final guide, which is final principle, that sometimes not getting what you want is wonderful. It's easy to spend a lot of time on a task and to arrive at failures. But if we fail slowly, we get through fewer tasks and our chances of success go down. This is just an encouraging principle that as part of your data preparation efforts, it's better to fail fast and to iterate. The more passes you have of something, the more likely you are to have success. This concludes our 12 principles of data preparation for ML and analytics. More easy to understand here are the typical terms we would use for them. As mentioned at the beginning, this is mostly about how we handle outliers. We need to understand and collect them, take those in the long tail and bucketize them and make sure that we verified any assumptions and clean data. We have Googler standing by to take your questions. So if you do have questions, please let us know. Thank you.
Welcome back. We are nearing the end of the Americas event, but fortunately, we still have time for questions before the final session. So, Rado.
Yes.
Because you're the only one here.
That's right.
One attendee raised a good point when they asked, can AI be used to just compute or also to understand? What do you think?
It's an interesting question. It's actually really interesting. The simple answer is that all any computer can really do is compute. Its clue is kind of in the name. No program will ever truly be able to understand. But the more interesting and more complex answer is that we train these programs on what to look at and what to do with what they find. Now, a complex training model can actually seem much more like understanding. Now, think about the Quick Live demo, right? Now, everyone got a chance to play with that at the beginning of the day. The AI program seems to understand what you're drawing and would probably be great in a game of Pictionary. However, it achieves that through a lightning-fast series of computations, comparing the image it has with millions of other images that it's been trained on.
So it's a little wordy. I think the point that Rado is making here is that there aren't really any limits on what AI can do. The only thing holding it back is the difficulty of training a program and the robustness of the training set.
Yeah, absolutely.
So early voice detection systems, for example, could only recognize voices from a particular region in the United States. And that was pretty bad. But even by the time I first joined Google, we still had a lot of distance left to cover. So I was actually asked to add my voice to the training set as a native speaker, English speaker who grew up in a southern U.S. state. Like it was a very particular dialect they were trying to get. Because at the time, they wanted to become better at understanding different pronunciations of the same word, like pen and pen. I think they're different, but not for me. And now the Google Home devices are even better than that. They can recognize heavier accents from non-native speakers simply because Google has been working hard to expand its training set.
Yeah, absolutely. I mean, it's funny, reading the transcriptions from Google Voice messages used to be hilarious. Now it's like, actually, they usually get it right.
That's what I wanted to say.
Yeah. So I suppose our final answer, if you put all of that together, is that AI can only compute, but with the correct training set and the right set of constrictions, it can seem to understand much more than that.
So I guess, yeah, we're kind of not answering the question, but we are answering the question. We're just doing that like hand-wavy thing where we don't love answering a question, but it is true. Like you decide how complex your computers are going to be based on how many tools you have to work with, and hopefully services like cloud can help you do more complex things at an easier level for you and your company and your coworkers. But at that same time, it is important to understand that we are crafting the meaning of understanding, and we're imitating what we think that's going to be. And so however you're choosing to model your data, what you're choosing to value and prioritize when you teach your algorithm to mark data in a certain way or to do a certain thing, you have the power to be like as intuitive as you can come up with.
Absolutely. It's important to remember that at this point, at least, we're not offering general AI. We're looking to be able to create specific solutions to known problems. And so that's a big challenge for data scientists and engineers, is to figure out what are the right constraints, what are the things that we're able to glean understanding from by having AI do the computations for us.
That is true. And it's also different because when we're talking at an event like this, we love to talk about very specific problems. We like to talk about examples we've already done in certain industries, but we also love to talk about the dream 15 years from now.
Absolutely. Now, we're going to take this opportunity to welcome back people from the session New Age of Manufacturing. Now, Joanna, question for you. As a continuation of what we were just talking about, we have a question here about how an AI can become more intelligent than just an if-then-else statement, or a large grouped collection of if-then-else statements.
So this is a good question, and it's still interesting because it hits that same point.
Absolutely.
Technically, computer programs are quite simplistic, and as programmers, as we've talked about, we're the ones who make them more interesting. So if you studied computer science at a school or university, you probably had to do some work with basic circuits in order to appreciate the beauty of programming.
Yes, understand
Professors
how
love
it works
that.
at the low level. Yes.
And if you remember, the main point of those classes is that technically, all a circuit can do is add.
Exactly.
That is the only thing that these beautiful motherboards we build can technically do. They can only add. one at a time, this bit and that bit. And that's it. And if you string together enough of those adders and you apply some arbitrary meaning to what that does, you can actually create the complex machines that we have today, as well as the complex programming languages we use to build on those machines. And if you carry that metaphor through, the if-then-else argument, you actually have two different avenues to go here. This boring one, where a truly complex nest of millions of if-then-else comparisons, the same way we have millions of adders that are all processed insanely quickly. But there's also this world where we're constantly assigning that arbitrary data, that value, the metadata, to an object. And if, say, a sentiment analysis program is able to tag a phrase with not just positive or negative, but slang usage, reclamation data, etymology notes, you can build a word map of that phrase that can offer the computer much more information to work with when it goes through that if-then-else flow.
That is a long and complex answer, but absolutely true. So basically you're saying, no, it isn't more than just if then else.
I'm saying no. But, I mean, not technically. So no, I'm saying no. But in actuality, we can create so many interesting and complex spaces for our AI to learn. And that's what we were talking about too as the IS team joined in. But it's like we have the today, the tomorrow, the next 5 years problem. We also have the 50 years from now. What are these going to be doing? In order to reach that point, we have to start with the difficult and tedious things today. And then we translate that into assembly language, and we translate assembly language into like hex language, and we translate hex language into like, COBOL and Fortran and punch cards. And then one day we get Python, and it's so nice.
Yeah, absolutely. And I think that's often what we're sort of dealing with, particularly around AI at the moment, where what we're building is tools that make it easier for people who aren't maths PhDs or don't understand how to write assembly language, to be able to find ways to devise solutions to those problems without having to manually build adders themselves, right? You don't have to build our own circuits, we don't have to build our own transistors. We can start using more and more complex, and we're able to use programming languages which are able to represent a lot more symbolically without having to understand exactly how all of the plumbing works underneath.
And it also means that if you can't find your exact help that you need, it might be that you have a use case that no one else has thought of yet, and so we might need to tweak our tooling systems, and that becomes just part of being in the community and being able to have these conversations and share ideas. We just so much inspiration and knowledge to grow from. We're so early in the stage, even though we've been talking about it for probably a decade.
Yeah, I mean, I think that's one of the most exciting things, is that we really are so early on, particularly in AI, and a lot of the cloud stuff, which we take for granted because it's like, well, we work at Google and cloud is kind of where everything happens. But for a lot of the industry, this is by itself, big data, working in the cloud, all of this is actually really new. And with AI in particular, it is really groundbreaking. So there's this great opportunity for people to, become part of the community, figure out what the underlying problems are together before it even becomes a question of how do they solve those problems.
So now we're welcome back to AI Track, and hopefully what you just missed is how exciting it is to be in this field. And so now we're just going to tell you about our final two sessions for the day.
For the final sessions, we have two great options to go away and check out. The Big Data Track will conclude with Scott Ellis's Putting Data Security and Privacy into Practice with Google Cloud. We talked a lot about security earlier, so this is a really interesting session. You'll want to check it out. We mentioned this talk earlier today, as I say. This is a great way to wrap the event for everyone interested in building great apps with confidence that their data is safe.
Exactly. And then we're combining both the AI and industry solutions tracks for the extended version of Quentin Hardy's Fireside Chat with Suzanne Johnson, Employment Branding Manager for General Motors, and Jessica Lee, Vice President of Global Talent Acquisition Strategies and Solutions at Merit International, to discuss how they are using artificial intelligence to tackle common business problems. Y'all have fun.